Alright everybody, welcome back. In this video we're going to look at some applications of integration. Specifically we're going to look at pumping work, the amount of work that it takes to pump a liquid out of a container. And if you read through the first page of this material, you saw the basic idea for setup, and you also saw a list of weight densities that we need to have. Typically myself, I tend to set up my integrals to do these as whatever the weight density of the liquid is. If I could spell density this morning. And then we'll integrate from the bottom of the liquid to the top of the liquid. And we've got the distance a typical slab must be pumped. Times the volume of the slab. Okay, so in example 1 here we're told that we have a cylindrical tank of diameter 4 feet. So the diameter here is 4 feet. And the tank is 6 feet high. And it is half full of molasses. Okay, so as far as setting up our integral, first I need the weight density of molasses. You can reference the table on the previous page. Find that the weight density of molasses is roughly 100 pounds per cubic foot. And then we're going to integrate from the bottom of the liquid to the top of the liquid. Now we have an option here, and we can set up our coordinate gridding system where we either set up the top as a height of 0 or the bottom as a height of 0. And we usually make that decision based off of which is going to be easier for the particular model. Since this is a cylinder, it's not really going to matter. The calculations are going to be almost identical. So I'm going to let the bottom of this be h equals 0 and the top be h equals 6. And so the molasses is running from height 0 to height 3. So those are going to be my limits of integration. And now I need the distance that a typical slab must be pumped. So let's think about a typical slab of molasses that's in here. It's going to be a very short cylindrical disc. But say I have the slab that's at height 2. In order to pump it out the top of the tank, that slab needs to be moved 4 feet. And the slab at the very top needs to be moved 3 feet. And the slab at the very bottom needs to be moved 6 feet. In general, we can come up with the expression that the typical slab needs to be moved 6 minus h feet to be pumped out of this tank. And then we need the volume of one of these very thin cylindrical discs. Well, it's got a radius of 2. It's got a thickness of dy. If you look at the slab from the front view, the thickness of the slab is dy. And so the height of this, or pardon me, the volume of this is going to be pi times the radius squared times the thickness. I'll call it dh since I'm using h as my variable. And simplifying this integral a little bit, I can bring the 4 pi out in front. And so in essence, to find the amount of work done here, I'm going to take 400 pi times the integral from 0 to 3. 6 minus h dh. And I'm going to go ahead and do that. 400 pi times the integral of 6 minus h dh from 0 to 3. 16,964.600. And we're talking about the work being done with feet and pounds. This is going to be measured in foot-pounds. and that's the amount of work to pump out all the liquid out the top of the tank in example 1. Alright, let's look at example 2, a little bit more complex. A tank in the shape of an inverted cone. Has a height of 15 feet and a base radius of 4 feet. It is filled with water to a depth of 12 feet. Now for this, it's going to be easier for us to set up our grid system with h at the bottom being 0, at the top being 15. And we're going to set up our expression. First off, I need the weight density for water. I'm just going to go look back at my table of weight densities here. Water is 62.4 pounds per cubic foot. So we'll put that into our formula, 62.4 pounds per cubic foot times the integral from the bottom of the liquid, which is at 0 on our coordinate system, to the top, which is 12. Then we need the distance that our typical slab is pumped, and that's going to be 15 minus h. So the slab all the way down at the bottom gets pumped 15 feet. The slab at the top gets pumped 3 feet. And then I need my formula for the volume of one of these slabs in terms of h. So realize we need the radius of the typical slab, because our formula for the volume of this is again going to just be pi r squared times the thickness. But what we need is we need an expression for r in terms of h. And so we need to generate an expression for r in terms of h. And this is actually reasonably simple because of the self-similarity of cones. When radius is 4, height is 15, and when radius is 0, height is 0. And so we have this self-similarity relationship where r is to h as 4 is to 15. And so solving this, we can find that the radius is always 4/15 of the height of where we are in the tank. And so that's going to be the r that we put into our formula to find the volume of the slab. And so the volume of the slab is going to be pi times 4/15 h quantity squared dh. And I can bring the pi out in front of my integral. But outside of that, I'm going to have to calculate this whole thing. And so I break out my hand again, calculator, 62.4 pi, and use the integral of 15 minus x times 4/15 x quantity squared with respect to x, 0 to 12, 48,177, and 655 foot-pounds of work is required to pump all the water out of this tank. So in general, when we look at this methodology, if you remember, we need 3 things primarily. We need the weight density of whatever the fluid is that we're pumping. We need to know the distance that that fluid is being pumped. We'll establish our limits of integration and that distance formula based on a coordinate gridding system that we set up. And then we need the volume of a typical slab of the liquid, which in a lot of these cases when we have cylinders or cones is going to be a short circular disc. So we'll find it by finding pi r squared times the thickness dh. And then we just need to come up with an expression for the radius in terms of h, because we need to have h in our integrand because everything's being integrated with respect to h. Okay? That's the end of the examples from this lesson and the end of this video. See you guys next time. Have a great rest of your day.